Okay, picking back up integrals of trigonometric or hyperbolic trigonometric functions to even powers at the moment. All right, so sine squared, you got to know this half angle formula like so. Well, I guess there's a way around this using integration by parts, but my goodness, I do think this is the fastest way to answer. Now, 1, of course, integrates to theta. Cosine 2 theta integrates to, well, minus 1/2 sine 2 theta. Of course, to check my antiderivative, all you need to do is to differentiate this term. Chain rule pulls out a 2, cancels the half, and leaves you with minus cosine 2 theta, plus a constant. All right, there you go. See, that wasn't too bad, was it? I guess not. There it is. All right. Let's see here, these guys are kind of important, so let me do both of them. Integral of cosine squared theta d theta. Well, that's the integral of 1/2 1 plus cosine 2 theta d theta. Now, if you think about it, if this is the identity for sine squared, that has to be the identity for cosine squared, right? Because when you add sine squared plus cosine squared, you get 1, right? So whatever you have to add to this to that to get 1 is what the identity has to be for cosine squared. And you see the cosines cancel. 1/2 plus 1/2 is 1, so it makes sense, you know? So if you know one of these identities, you ought to automatically know the other. And if you think about it, you should be able to figure out the minus has to go with the sign, because sine of 0 is 0, and if you plug in 0 here, you get 1 minus 0, which is, well, 0. So the plus has to go with the sine squared. Excuse me, what's wrong with me? The minus has to go with the sine squared, obviously. All right. So 1/2 theta minus, plus 1/2 the sine of 2 theta, close parentheses, plus a constant, and there it is. That, folks, is the integral of cosine squared. And, well, integrals of higher things, a little bit of a pain, but really nothing too much to stop us. For example, if I want to integrate, let's say, cosine to the 4th theta, d theta, right? Well, that's the integral of cosine squared theta, quantity squared, right? And so that's the integral of 1/2 1 plus cosine 2 theta, quantity, close brackets, squared d theta. So I'll pull 4th out, 1/2 squared squareds to 1/4. And then I got to square this thing. That gives me 1 plus 2 cosine 2 theta plus cosine squared 2 theta, like so. Like, oh man, look at that. I got a cosine squared. Now I can either, if I happen to have this fresh on my mind, I could just do like a u substitution on this thing, but I'm going to do it directly. So 1/4 integral of 1 plus 2 cosine 2 theta, and then plus 1/2 1 plus the cosine of, now if I'm doing cosine squared of 2 theta, 2 times 2 is 4, so I put a 4 theta here. All right, and then close big brackets, d theta. All right. Now, one more step here, because I have a tendency to mess up the arithmetic here. All right. So let's see here. I'll leave the 4th out front, and that's going to be 1 plus 1/2 is otherwise known as 3/2. All right. So 3/2 plus 2 cosine 2 theta, right? Plus 1/2 cosine of 4 theta d theta, and now I will do the integration, and I will foolishly attempt to multiply the 1/4 through at the same time, because I don't know better. All right, so this is going to give me 3/8, and d theta integrates to theta. 2 over 4 is 1/2, right? But cosine pulls down another half from the u substitution, because it's cosine 2 theta. So I get plus 1/2 times 1/2, let's see here, 1/4 sine 2 theta. 1/2 times 1/4 is 1/8, but then there's a 4 that pulls down from the u substitution here, a 4 theta, so we get 1/32. So plus 1 over 32 sine of 4 theta plus a constant. And there you have it. That is the integral of cosine to the 4th. Now, nothing stopping us. We could do cosine to the 6th, or the 8th, or the 10th. And we can do sine to the 4th, and sine to the 6th, and sine to whatever power your heart content, desires. But since you guys aren't paying me enough to do this, I'm not going to do it. But anyway, you could do it. All right. So I don't know if you're keeping track of things, but we got even, we got odd. So I do believe we have all possible integer powers, natural number powers of sine and cosine. We can do those integrals. So let's see here. I guess I talked about odd powers of cosh and sinh. How about even powers of cosh and sinh? So hyperbolic, I need a little bit more hyperbolic identities that you may or may not know. So I think I may have derived one of these. Let me see here. So like sinh squared. Sinh squared, I'll use theta. So that's 1/2 of e to the theta plus e to the minus theta. Oops, that's supposed to be a minus. It's sinh, right? And so I got to take that thing and I got to square it, right? All right, so you square this thing. Squared. And so what that gives me, of course, is 1/4, right? And then e to the theta times e to the theta, e to the 2 theta, minus e to the theta times e, I'll write it out, e to the minus theta, minus e to the minus theta times e to the theta. Think about foiling it out. Or don't, if you don't, I don't know, whatever, however you want to think about multiplying it. It's your business. Minus 2 theta. Anyway, when you multiply it out, you get these four terms. And, of course, I can pull out a half, right? And then on the one hand, I've got 1/2 of e to the 2 theta plus e to the minus 2 theta, all right, from this guy and that guy. Now these, that's 1, this is 1, so I've got minus 2 over 4, right? So in other words, I have minus 1 here, right? Because these two terms simplify to minus 2/4, which is minus 1/2. Multiply this back out, you also get minus 1/2, so you can see that it's even Steven, or whatever you want to say. 1/2, it's fair game. 1/2 of, well, that's cosh. Lo and behold, cosh 2 theta. Minus 1. All right. So there you go. There's a handy-dandy identity for the hyperbolic sinh squared. There's the double angle for hyperbolic sine. That is what it is. All right. Now, the double angle formula for hyperbolic, I mean, you can do various things with this. I'm trying to remember, if I have a plus here instead of a minus, what's the difference? Almost the same calculation. You can kind of even see it with this right here, right? Same song and dance, it just changes this to a plus, right? And changes this to a plus, and changes that to a plus. Otherwise the same. So we get cosh squared is, what is it? Well, it's 1/2 of cosh of 2 theta plus 1. Now, let's see here. Does that make sense? I think it does. You can check these two identities unboxing in green. If they're legit, we should be able to see what? We should be able to see that cosh squared theta minus sinh squared theta is equal to 1. And you can pretty easily see that if you take this formula and you subtract that formula, the cosh 2 thetas cancel, and you get 1 minus a minus half, which is otherwise known as 1. So, ka-ching, there we go. Now, if you want, you can get yet more identities from differentiating these. I think I mentioned this before. This differentiates to give me 2 cosh theta sinh theta, right, is equal to what? On the other hand, I get 1/2 of 2 times the sinh of 2 theta, right? So therefore, sinh 2 theta is equal to 2 cosh theta sinh theta, right? Now, I don't know if you know this or not, but there is a well-known trig identity which says that the sine of 2 theta is 2 cosine theta sine theta, right? It's one of the more famous identities for the sine. So anyway, there's a wonderful and well-known correspondence between cosh, sinh, sine, and cosine, which comes into full view, complete clarity when you study complex analysis. All right. But anyway, we see most of the iceberg right in front of us here. Anyway, once you have these, it's pretty obvious that you can integrate, right? What example was I on? Example, I don't know. What's my numbering? Example 3, 4, 5, 6. Where am I? 6. Okay, it's example 7, I guess. I don't know. So to integrate, come on, integrate even powers of cosh or sinh or whatever. You use these identities. For example, if I was going to integrate, I'll do a u substitution on top of things. How about that? Cosh squared of 3x. Ooh, tricky. Dx. Then what I would say is, aha, I know my handy-dandy cosh formula, so that's 1/2 the integral of the cosh of twice the angle of the original thing, which is 3x. So I put myself a 6x here, plus 1, parentheses, because I like to be correct, dx. And then, so what do I got? I got 1/2. Cosh integrates to 1/6 sinh of x, because this inside 6x, I have to do a u substitution there implicitly, plus x, close parentheses, plus a constant. I'll clean things up a bit. Well, I mean, you can decide whether you think that my final answer is better or worse than the step above. I think it depends on where you're raised, I guess. I don't know. All right, so there it is. And if you've been following along here, you really shouldn't be surprised that I tell you you can easily integrate cosh to the 4th or the 6th or sinh squared or sinh to the 6th and so forth and so on. If you understand what we just did and the power of these two formulas, well you know, come on, you're good to go. All right, so let us turn our attention to a more nefarious foe. Another can of worms would be what? And here I'll probably just, at the moment, I don't know. How about the secant and tangent? I think I may put off hyperbolic secant and hyperbolic tangent for Calc 2. Gotta leave something. All right, so secant. First of all, the easy example, example 8. This one, you better know. Secant squared theta d theta. All right, so you're like, yeah, that is tangent theta, woo, plus a constant. Likewise, the integral of tangent squared theta, right? We talked about this one before. That's the integral of what? Remember, key identity. Key identity for working with, there really are several key identities. Algebraically, the key identity is that tangent squared theta plus 1 equals to secant squared theta. And there's two differential identities we must keep in mind. The one is that the derivative of secant theta, right, is secant tangent. And the other one is that the derivative of tangent theta is secant squared theta d theta. This trifecta of knowledge will solve your problems. Well, when you combine it with some common sense, I suppose. Tangent squared is secant squared theta minus 1. So, yeah. That then is tangent theta minus theta plus a constant. All right. All right. Now, let's dial it back a step here. Example 9. I'll do the easy one first. The integral of tangent theta d theta. Actually, a very good example of u substitution. This is the integral. This is the one where my trifecta really is kind of irrelevant. Actually, the next one too. in fact, odd powers of sine, excuse me, odd powers of tangent or secant, well, we shall soon see. They bring the pain. So sine theta d theta divided by the cosine theta, oh, okay. Well, that's nothing more than the integral of d of cosine theta, right? Over cosine theta, except the derivative of cosine theta is minus sine theta d theta. I could put a minus out here, but yeah, there you go. Minus the natural log of the absolute value of cosine theta plus a constant, or as you're sometimes often see it, the natural log of the absolute value of secant theta. Secant's 1 over cosine, right? So bring the minus in, reciprocates the argument, the exponential, and there you have it. Our handy dandy integral of the tangent, natural log of the absolute value of the secant theta, plus a constant. Very, very popular integral. Now, I guess I'll make it its own example because it is, after all, well, yeah. Integral of secant theta. So you go, huh. Well, I think if you look at that, you can see that that is clearly the integral of du over u, where u is equal to secant theta plus tangent theta. I am being facetious here, folks. It is by no means clear that that's true. I happen to know it because I've done it a few dozen times. But anyway, let's check it. So like du, I'll do du d theta. You're like, hey, finally. Du d theta, well that's secant theta, tangent theta, plus secant squared theta, right? Factor out the secant theta. And then we've got a secant theta, well we got tangent theta plus secant theta in my current ordering. Aha, well that's exactly u again, right? So there you have it, du over u is equal to secant theta d theta. Woohoo! Alright, so there's your little thought bubble. Actually, it's a magical bubble because I didn't explain to you. I have, my wife claims that it's, clear that u should be secant plus tangent if you just play with it for a little bit. But most students I know and have contacted with do not play with integrals like my wife does. Natural log, I don't. Natural log of the absolute value of u plus a constant. Alright. That's the natural log of the absolute value of secant theta plus tangent theta plus a constant. This should be a little bit unnerving. I mean, where did this u substitution come from? It's just bizarre, right? Now there are other ways to derive this with partial fractions later. Probably you can derive it with integration by parts. Everything can be derived by integration by parts if you're sufficiently persistent. But there it is. Now, I will just tell you, the integral of secant cubed is not pleasant. All right. Integral of tangent cubed, I don't know. That's about as far as I want to go here for now. Of course, we can mix and match, right? You can do some funnier stuff like I don't know. Let's see, example 11. Of course, we have hyperbolic analogs that are pretty simple, like the integral of hyperbolic secant squared of 3x dx. What's that going to be? I don't know. Here, let's check it out for a second here. Cos squared x minus sinh squared x is what? It's 1. So if we divide this by cos squared, we get 1 minus the tanh squared x is equal to hyperbolic secant squared x. All right, well that's fun fact, all right? Let's see here, what's the derivative of hyperbolic tangent? I forgot, all right? Derivative of hyperbolic tangent is, oh, I'm starting to remember now, that's d dx. I do think I did these in these videos already. Sorry, I'm repeating it. You're like repeating something when you teach? That's crazy. I know. Well, these are reviews, right, folks? Although I don't tend to repeat myself that much. I'd rather say it once correctly. Now, that's going to be cos x minus sinh by the quotient rule divided by cos squared. But that's cos squared minus sin squared, which is 1, so yeah, you got hyperbolic secant squared x. All right, so there, just refreshing my memory. All right, great. So, long story short, this is nothing more than 1/3, right? Hyperbolic tangent of 3x plus a constant, because we can just make a simple u substitution, and the integral of secant squared is hyperbolic. Hyperbolic secant squared is hyperbolic tangent, and that's it. Now, of course, if you were to face an integral like, I don't know, hyperbolic tangent squared of, let's say, 3x plus 2, right? What would that be? Well, that would be the same as the integral of, let's see here, solve for hyperbolic tangent in my identity. You get that's 1 minus the hyperbolic secant squared of 3x plus 2, right? So that's by a little hyperbolic trig identity. I just solved this identity for tangent squared, and it gives me 1 minus hyperbolic secant squared. Now, finishing blow here, let u equal to 3x plus 2, so du is 3dx, or in other words, dx is equal to du over 3. Well, that's not too bad. So what I got is I've got 1/3, right, of what? Of, this is going to integrate to, oh, sorry, I made one more step. I'm kind of cramped here for room. So I'll pull the 1/3 out front. Now that gives me 1 minus the hyperbolic secant squared of u du. All right, so that's 1/3 of u minus the hyperbolic tangent of u plus a constant. And then finally, that's 1/3 of u was 3x plus 2 minus the tangent of 3x plus 2 plus a constant. All right, and there it is. All right. There's probably more. I'm sure we'll run into further integrals of trig functions as we study calculus 2. This should get us started pretty well. I mean, this is a pretty good cross-section of trig and hyperbolic trig integrals of an elementary nature, which you can do without integration by parts. You can just do by basically, having a good mastery of the, the identities. So, I think, unless I'm forgetting something, that's about it for the basic integration. I've got a couple tests that I'll try to talk you through the solution of, and I think if I missed anything terribly significant, it ought to be in those tests, so I'll let that pick up the slack. Our next thing I'm going to talk about, of course, is going to be the problem of area, and the Riemann sum and the definite integral, along with the breathtaking magic of the fundamental theorem of calculus. A truly remarkable result, which we do not appreciate enough. Anyway, thanks guys.